We have been talking about limits, and I've talked to the concept of what a limit is, and I've spoken to the concept of what an infinite limit is and how to deal with that. There's just something on my computer and I'm trying to clean it off. That's why I'm staring down here. I know you're wondering. So the question then becomes, what do we do with these limits? And as we're thinking about that, we have to talk about the concept of a left and a right hand limit, because it's going to become important to us when we define continuity. And we have to define continuity in order to find the derivative, because if something has a derivative, which we're going to get to and eventually we'll understand what that is, it has to be continuous in order for it to be differentiable. That is, you can't take the derivative of something unless it's continuous. And in order to understand continuity, we have to understand limits. And particularly, we have to understand left and right hand limits. Now, we've talked a little bit about this already, but I just want to delve into it a little deeper, particularly about piecewise functions, because that's something you guys have not seen a lot of. So we've already looked at this. When direct substitution results in k over 0, we've already looked at that, the left and right hand limit in terms of a table. And if you look in the video about infinite limits, you'll see that. We haven't talked much about this, absolute value expression, so we kind of want to highlight that. And we haven't talked too much about radicals, so we're going to highlight that a little bit. And then particularly, I'll make this circle bigger, we're going to look at a piecewise function. So what is a left hand and right hand limit? First of all, well, we know that already, again, if you watch the infinite limits video, but the left hand limit is a number that's a little bit less than what x is approaching. So if x is approaching a from the negative direction, we say, then it's coming in less than a. It doesn't necessarily imply the number is negative. If that number is 3, then a from the negative direction just means 3 from the negative direction, which could be 2.9, 2.99, and then 2.999. And as you get closer and closer to 3, you're coming in from the negative direction. So it doesn't necessarily imply that it's negative. It just means it's less. And then, of course, the positive indicates that it's the right-hand limit, and you're coming in from a little bit more than the number. So just, again, to sort of explain, if that's 3, then we'd be going 3.001, 3.01, and 3.1 kind of thing. So we're coming in closer and closer to 3, but from something bigger than 3, just as an example. So that's what it means, and I think we are fairly clear about that concept. So where does it apply? And what happens is, the reason that it's important is if these two limits are not equal, then the limit doesn't exist. And we've already talked about that, again, about infinite limits. We've said sometimes it's going to go to positive infinity, sometimes it's going to go negative infinity, sometimes it doesn't exist, those kind of things. So it is possible to have a left and right hand limit that are equal, but if it's not equal, then we can say the limit doesn't exist. So here's an interesting idea. If you take the limit as x approaches 0 from the positive direction of root x, the answer is 0. And the reason I can say that is because if I plug 0 in here, I can just go the square root of 0, and that's equal to 0. But the limit as x approaches 0 from the negative direction does not exist. And you might be saying, well, why not? Well, if you think about the graph of root x, it actually starts at 0, 0, kind of goes up like this, right? But there's nothing over here. It's completely empty. So I can't approach from the negative direction because the function doesn't exist there. And the reason it doesn't exist there is because, let's say that's -2. If I try to plug in the square root of -2 and say, wait a second, that's not a real number. Does it have a value? Yes, we've talked about that. We don't want to say you can't take the square root of negative at all. You can, but it's not a real number. It's an imaginary number. So what that means is I can come in from bigger than 0 and I go to 0. I can come in from lower than 0. Wait a second, no, I can't. So because of that, the limit as x approaches 0 does not exist for root x, because these two values are not the same value. This one doesn't have a value. So that's an example of a square root, and that happens wherever the square root goes into the negative. So if it was the square root of x plus 2, then that would change to -2. It would sort of back it up, right? But wherever that square root becomes negative, we have a problem if we're trying to approach that number, below that number, because the function's not there. All right, so that's an example of a square root. Absolute value, again, is not something we necessarily talk about too much, but it is something to keep in mind. And absolute value, we know it just changes things that are positive to positive. So really, it has no effect. So when x is bigger than 0, I'm going to jump over this one for a second. The absolute value of x and x are the same thing. But when x is negative, then the absolute value takes that negative and makes it positive. So we can actually describe the absolute value of x as two separate functions. We can say the function is equal to minus x if x is negative, that is x is less than 0, and it's equal to x if x is greater than or equal to 0. If I want to know what's going on at 0, then I have to plug 0 into this and to this. Okay, so I have to look at the two limits. So I say, okay, the limit as x approaches 0 from the negative direction of absolute value of x is, we're saying, again, negative direction does not necessarily mean negative. It just means we're coming in from less than 0. In this case, it does mean we're actually coming in from a negative number. So what we do is we go up to our piecewise function. You say when x is less than 0, the function is described by minus x. So I plug 0 into minus x, and I get 0. Now, if I'm approaching 0 from the positive direction, that is described by x. That's the portion of the function. So I put x in there, and I also get 0. So what that means is they both approach 0. The answer is 0. All right, and if you look at the graph of absolute value of x, you can see that. Okay, that's what the graph of the absolute value of x looks like. That's the part we're describing as y equals x. This is describing, or this is what is being described by y equals minus x. And you can see that in both directions it approaches 0. Okay. So that's an example of an absolute value. Here's an example of a piecewise function. And a piecewise function is not something you're necessarily used to, but what we're doing is we're describing a function in 3 different pieces. We're saying this piece, the function is minus x minus 2 if x is less than or equal to minus 1. Then from minus 1 to 1, it's x. And then after 1, it's x squared minus 2x. So to give you kind of an idea of what this looks like, we're drawing minus x minus 2. So that's a line that goes through minus 2. If this sort of imaginary line kept going, it doesn't, but if it kept going, it would go through minus 2, right? And it has a slope of 1. So you go over 1, back 1, slope of negative 1. So you go over 1, back 1, sorry, back 1, up 1. There we go, back 1, up 1, and you kind of get your idea. But then at minus 1, it switches. Now what's interesting is at minus 1 here, if I just focus in on minus x minus 2, if I put in minus 1 times minus and then minus 2, that gives me 1 minus 2, so that gives me minus 1. So this at minus 1 is minus 1, and this at minus 1 is just x, so it's also minus 1. So what that means is there's no break. That is, there's no difference whether I'm at minus x minus 2 when I'm at minus 1 or I'm at x. They both have the same value. So you'll notice there's nothing bad about that particular point. And then it goes up y equals x. So it goes up like this until it gets to 1. When it gets to 1, we now look at these two functions. So when it's at 1, I'm just going to change the color so you can see when x is equal to 1, I plug it in first of all into this. So I'll say that's 1. And then I plug it into x squared minus 2x. So I go 1 squared minus 2 times 1. That gives me 1 minus 2. That gives me minus 1. You notice they're different. Now, when x is equal to 1, it's described by x. So that's why down here I've colored that point in. But then it jumps down here and becomes quadratic. Okay? So once we've drawn the graph, we can kind of see what the limits are pretty easily. So let's say I want the limit as x approaches minus 1 of f of x. The answer is, according to our graph, we can see it's minus 1. If we didn't want to draw the graph, we could do it by looking at these two functions. Okay? So what we'd say is, all right, I want the limit as x approaches minus 1. So I take the limit as x approaches minus 1 from the left, that is my left-hand limit, and that is described by this, because when x is less than minus 1, it's that function. It's minus x minus 2. So I plug in minus 1, I get minus 1. Okay, and again, I just did that up there, but if you want to remember what I did, I went minus 1, minus 2, and that's what gave me minus 1. Then I take the left-hand limit's done, so I take the right-hand limit. And again, I look at, okay, when x is bigger than 1, well, bigger than minus 1, it's being described by x. Okay, so the limit as x approaches minus 1 of x, and then we just plug in and we get minus 1. So because these two things are equal, that's why we can say that the limit of f as x approaches minus 1 of f of x is minus 1. All right, so it's these things become important in a continuity discussion, but you have to understand left and right hand limits first. Now, if we look at the limit as x approaches 1, we can see that as x approaches 1, it's going up to 1 if you have the left hand limit, but it's going down to minus 1 if you have the right hand limit. So, again, left hand limit, negative, it's x, it's 1. Positive means right hand, which means that function, which is minus 1. So since the numbers are different, that doesn't exist, and you can see it graphically. So that's the concept of a left and right hand limit. Okay, important to understand as we get into continuity. I'm actually going to end the video here and make another one just because of time to look specifically at continuity. So I'll be right back.